I'm going to discuss one or two scientific. No, one is astrophysics, and the other one is like numerical weather simulation. Yeah.
All right, we are officially Berkeley time, going into continuous time all the time. It's my pleasure to have David here. I've been wanting to host him for a talk. So I love David's work because he really works at some of the fundamental issues in machine learning modeling, and and I'm biased because he's very interested in science, and he's done some of the pioneering work in machine learning methods for chemistry. In particular at the intersection of graph and convolutional neural networks. But so he's originally from Manitoba. Who knows where Manitoba is? Very good, very good. We got some Canadians. But he did his PhD at the University of Cambridge. And he's been at the University of Toronto for how many years, actually?
7 years.
7 years, where he was one of the founding members of the Vector Institute. And that's where he currently is. And he's now an associate professor. And I'm looking forward to hearing about his latest vision for where these kinds of models can go.
Wonderful. So
you have your own mic.
yes, I might. How do I sound to you guys all? Beautiful. Okay, so I'm really excited to be here, and I really hope that I can carry everyone along for the talk. So I'm going to cover a lot of different areas of, let's say, differential equations, approximate inference, neural networks, scientific applications. Please raise your hand when I lose you. And I might not be able to stop, but I at least want to know. If you're here, the audience is always right. So if you're here, I want you to understand the main thrust of what's happening. Okay. So what I'm going to talk about today is a question that, well, I may be kind of known as the hype guy for null ODEs, kind of like maybe like Ian Goodfellow was for GANs or something like that. But I really try not to be that person, even if I'm incentivized to be them. And so I'm going to try to give you an honest assessment of when should you use continuous time methods in machine learning, supervised learning, and like time series modeling and a few other domains. And honestly show you the pros and cons of this sometimes exciting, sometimes not worth it set of tools. Then I'm going to focus on one particular setting that I do think is worth using this set of tools for, and that I've been pursuing for the last couple of years, and I am very excited about for a number of reasons that I'm going to get into. One thing that I've managed to do regularly in my career is piss off adjacent fields that I'm borrowing methods from. So if you are a numerical methods person and you think I'm making an irresponsible claim, please, I can handle it. Tell me that is not a well-posed problem or whatever it is. I want to know. I'm not trying to be the deep learning know-nothing. Okay, so, and then I'm going to talk a little bit about where I'm going with this, some more experimental stuff. Great. So because this is a CS audience, I did not study ordinary differential equations in my formal education at all. Luckily, there's actually not that much you need to know as long as you're not going to ever solve special cases by hand. So that we're all on the same page notation-wise, we're going to assume that there's some state of a system. We'll call it Z. It could be vector valued. This could be like the concentrations of different chemicals in a system or position and velocity of planets in a solar system. There's going to be some function f that says how does this state change instantaneously through time? And it gets to depend only on the current state and sometimes also the time. We can draw this the direction at every point, and we get this nice sort of field of gradients. And the spoiler alert, we're going to be using a neural network to specify this function. And that's sort of the main thing we're going to be doing in this talk. Usually, once we've specified one of these differential equations, what we're going to do with it is take the state at some some initial time. You can see the little tiny dot on the left there. And then follow the gradients to find what the trajectory would be of that system if it started in that state at that time. So one important thing that I want to do that isn't always done with differential equations is to keep them in continuous time and to not discretize them. So often the easiest way to start working with a continuous time system is to first choose some discretization like every second, and skip all the time blocks in between, maybe doing my updates with something simple like Euler steps, which say we can approximate the step at some time 1 delta ahead by just following the current gradient for one step. However, there's no good computational reason to ever do this because we have really good adaptive solvers that were developed by the numerical methods community over the last 130 years or so. And what these will do is they will try to extrapolate where the trajectory is going, monitor how much error they're accumulating as they go, and adjust their step size so that when the dynamics are simple, they can make long steps. When the dynamics are complicated, they can take lots of little steps and really make sure they're getting all the details right. And this is a really cool family of like adaptive methods that we don't really, I think, have great alternatives for in machine learning in general. Although some approximate inference methods maybe could be said to be doing the same thing. All right, any questions so far? Great. So now I'm going to get into the original reason why people were excited about, well, neural ODEs and bringing some of these methods to deep learning, which is that you can construct a family of deep neural networks out of these adaptive ODE solvers. So I'm just going to walk you through the recipe for doing that really quickly for those of you who are too young to remember NIPS 2018. Okay, so this is a little pseudocode of a residual network, which is sort of the standard backbone of most deep networks. Sorry, this is the standard backbone of a standard multi-layer perceptron on the left here, which is that we have some input x as the input to our neural network. It gets updated by some layer f to give us some hidden units. Then we feed those hidden units into another function. We get some second hidden units. We keep doing this over and over, and in this way, by composing several simple functions, we can specify some complicated function. It's just function composition. But this turned out to be hard to train with gradient descent. Oh yeah, and these functions are going to be some very simple parametric family, like we multiply the input by some family or some weights, take some nonlinearity, and multiply them by some other weights. Again, just to be concrete. It turns out to be easier to train these methods if we have a slight twist, which is that we put the input through a function and then add the input back in. And I would say there's not really any great justification for this other than it just makes it easy to train deep networks. You can sort of get an intuition for this if you look at how gradients are less likely to vanish or explode as we make things deeper. So anyway, this is kind of, or at least in 2018, was the state of the art in general neural network design. And we can say this kind of looks like that Euler rule that we looked at before, where you take the current state and then you add some function of that state to get the next one. So that's the first hint that this kind of could look like an ODE if we really wanted to. So here's a figure trying to show what that looks like. So here I've replaced x with z, and we can imagine defining our little dynamics function, f of z and t and some parameters theta, as just calling a neural network with that z as input according to the parameters for that layer. Okay, and so these little arrows will show what direction that f moves our state in at each step, and we could define a ResNet as doing a little for loop over every layer, updating the hidden state according to that that layer's parameters, and we get this little kind of trajectory of hidden units being updated. And the whole point here is this is just a soup of computation that has some specific parameters that we can tune to learn some mapping from the inputs at the bottom to the outputs at the top. Yes, Jacob. Sorry, so NNet is like that little, one tiny little layer of yeah, where did I put that guy? Sorry. Yeah, so at the bottom here, we could view this as just one hidden layer of a neural network. Yeah, at some point we have to bottom out. We can't just keep defining neural networks inside of our neural networks forever. Great. Yeah, so the idea is that this little neural network is some very simple block that we're going to compose. Okay, so now how can we make this into some sort of continuous time block that we can use to take advantage of all these adaptive solvers? So I'm just going to make a slight change. I'll go back and forth a little bit so you can see. So, oh, sorry. too much back and forth. Okay, so originally we had our f, just evaluate the neural network at this z and at the parameters according to that layer. So we have a list of parameters, one for each layer. Now we can say, what if I actually just say the neural network takes in another scalar, which is the time, which is like here, that's the depth, and has one fixed set of parameters for all layers. But those parameters specify a slightly larger function, which can vary with time. So now I could evaluate this f function in between layers. Right? This t used to represent an integer layer number, and now it's this sort of notion of it's the depth that we're evaluating this network at. So far we haven't really gained anything. We've just slightly reparameterized our neural networks, and we can still solve them with this Euler solver, and we would still have standard ResNet-looking things. But because we've put them in this framework that is compatible with, like type compatible with ODE solvers, we can replace that Euler solver with just some call to some black box adaptive step ODE solver like Runge-Kutta or Adams or whatever. It doesn't matter. The point is the ODE people can think hard about how to take long steps when it's possible, and whatever they come up with, we can stick our little learned dynamics function in it. And now when we want to evaluate this neural network, instead of just having our fixed number of steps, we instead start at time 0 and ask the ODE solver, hey, just evaluate this vector field wherever you think you need to tell me where this trajectory ends up at the end. Cool. So, and now the number of layers of this network is not something fixed ahead of time. It's like a detail that's left up to the solver, and we can adjust it by, for instance, changing the error tolerance of the solver. If we want a quick approximate inference, we give it a loose tolerance. If we want a really precise answer, we can give it a very tight tolerance, and it'll evaluate this trajectory more finely and give us maybe a slightly different, better answer. Okay, so that's the whole trick. Any questions about this? Cool. Okay, great. So if we want it to be hypey, we could call these things on the right infinitely deep neural networks, because really they're taking these sort of like infinitely many, infinitesimally large steps. And again, like the number of function evaluations depends on our tolerance and how complicated the dynamics are. So here, here's a few different starting points where we start the solve. And the ones with lots of bends require lots of evaluations. The one here in the middle where everything's straight requires few evaluations, right? So this is great. This is something we want from our artificial intelligence, is think hard about complicated problems and not think hard about simple problems. Okay, so now I'm going to try to I don't know how much I've hyped this up in your mind, but I'm just going to try to now give a more realistic assessment in the cold light of a few years later, what actually of these hypey promises paid off and which ones didn't. Yes, Jacob. Oh, great question. So yeah, where do these Fs come from? The short answer is wherever people got them for their ResNets, we can just use almost the exact same architecture, except we have to take in one extra scalar, which is the time. Oh yeah, great question. So yeah, here on the ResNets, we have different parameters at every layer. Here I said that we kind of share them. So there's two answers. One is sometimes in residual networks, people don't have totally separate parameters. They have a hypernetwork that is like an RNN or something that outputs parameters for each layer as the output of some other smaller neural network. And so you can basically do the same thing here, where you have a little hypernetwork that takes in a scalar time as an input and outputs the weights for that output time. But ultimately, because of universality, it usually doesn't matter that much, which one of these we use. Cool. Okay, so at the time, people were excited about this because we said, okay, this can be some adaptive replacement for residual networks, right? And we can, every place you have this residual network, which is like the workhorse of supervised learning, you can replace it with this adaptive thing. Also, it turned out that going to the infinitesimal limit meant that you could fit or make different versions of normalizing flows, which is a density model. Like if you want to fit density of some data, you have more options when you go to continuous time. And the final one was natively continuous time series models, which is what I'm going to talk about later. As I mentioned before, one of the cool things about these methods is that you can tune the tolerance so that you can spend a long time thinking and get a very precise answer, and like maybe that'll have like low classification error, or spend a small amount of time thinking and have less accurate results. But the point is, normal neural networks just choose a point on this Pareto front, or well, let's just say some fixed trade-off between these two things. And you can't at test time very easily change these. You can play with like your floating point accuracy and stuff like that, but that's kind of a blunt instrument compared to this like fine knob that we can tune. Yes? Yeah, exactly. So the idea is that we train the network once, usually at some like, well, we can start with a loose tolerance at the beginning of training and then like tighten it over time. That's another advantage. But then the idea is this plot is from a single network that's been trained once, and then we're just loosening its tolerances.
So there's this like deeper that you make more accuracy. How much of that is just how much of that is
sorry, I'm not quite sure I understood. What are you saying that we gain from having a smaller time step?
Technically, we're supposed to use
Oh, cool.
this, so the recorded version will.
so generally in order to get higher accuracy we use very right?
Yeah.
Well, how does that using like in the solar
I see.
gains that we normally see in normal come from kind of behavior?
Yeah, that's a great question. It's like, how much computation do we gain by taking, there's some sort of like notion of the computational capacity of these networks that's very easy to quantify on the left. It's a lot harder to quantify on the right. And actually, there's a guy in France whose entire life's work is continuous time complexity theory. And he actually has, I think convincingly to me, shown that the length of the trajectories, like measured in terms of their output space, is the continuous time analog of like circuit depth. And so it's kind of like a weirdly unknown line of work in my opinion. But that's all that is to say, I don't think I could make a very hard quantification of how this number of evaluations relates to like a fixed network size. But I guess I would say you probably can get more bang for your buck out of the fixed number of layers than the one that's adaptive, because each fixed layer can kind of specialize more in general. Yeah. Okay. So this is one of the reasons we liked them. And then I'll just say, oh, yes.
Hang on.
Oh, that's so cool.
Hi. So there's also the notion of deeper networks overfitting, right? And if you have a network that can adaptively choose what its depth is, how would that network behave in training dynamics?
Yeah, that's a great question. So the effective depth, like the number of function evaluations that the network takes during training, usually increases with time. So it's like the depth is sort of automatically increasing. And we did actually run an experiment to address what your question is. I would say we didn't find a very strong relationship between the level of overfitting and the number of function evaluations that these continuous time networks are making. But obviously, if you're only making one or two, you have like a simpler model in some sense.
Right.
Okay, so to pour cold water on this idea, there was an amazing sort of, I don't know, like follow-up work from Zico Coulter and his group that said, we can get all the benefits of these ODE nests, these like infinitely deep networks, with a slightly different formulation that has some advantages. So he kind of like intellectually refactored this contribution into the important part and then a bunch of parts that we don't need. So his idea was to say, instead of specifying the output of our network as the solution of an ODE solver at final time, let's specify it as the fixed point of some of our neural network layer. So it's similarly, we're kind of implicitly defining the answer. We have to run some iterative procedure to actually get it. But then this gives us all the benefits that we had from ODEs, which is we can tune the speed versus precision of our fixed point solver. We can decouple the amount of compute from the number of parameters in our model. And also it can be adaptive per instance. And something we spend a lot of time in the paper talking about is the amount of memory you need to train these blocks is constant. You don't actually have to store all the intermediate steps of the fixed point solver or the ODE solver to get the gradients. But in general, fixed point finding is just an easier problem than solving ODEs. And one intuition for why that's true is that we don't actually care about the entire trajectory of the ODEs we're using in these sort of like infinite residual networks. We only care about the final point. But ODE solvers really care about getting the entire trajectory correct. In fact, they kind of have to. Whereas the fixed point solver, it doesn't really matter how it gets there. So they have like more freedom internally to do different things. Yes?
Doesn't this lose the residual structure? Because ODEs sort of are implicitly residual networks, but here, unless F is somehow like actually Z star plus F, then you're kind of losing that.
Yeah, that's a great point. So we do lose the residual structure. And maybe this is like too strong of a statement to say unqualified. This is basically empirically, this is generally true. There might be situations where like an ODE network, for some reason, happens to be a slightly better inductive bias. I will say that Zico Coulter did spend a lot of time trying to parameterize these networks in such a way that the fixed point was unique and that you knew that you would like converge to it. So it has its own issues. Yeah, anyway, I hope that answers your question. Cool. Okay, so that's like the sort of first negative result and the sort of like anti-hype slide. So the second reason why people were excited about neural ODEs is that there's this cool property that if a variable is changing according to some ODE, if this variable is a random variable, the density of that variable also changes continuously in time according to some ODE that depends on the trace of the Jacobian of this the dynamics function, which is something that is like very easy to compute. The standard change of variables formula for discrete time operations requires the determinant of the Jacobian, which is like a cubic operation, nonlinear. It's hard to approximate. This is like a special case of Fokker-Planck. This is not like very new math, but it sort of hadn't been exploited at this time in any systematic way. And this is really nice because now we can use some neural network to specify some vector field that maybe changes with time and show how this continuously changes some initial known density, like a Gaussian, into some arbitrary density that we can learn from data. So here we've learned from some data that's shaped like a maple leaf to approximate it by taking a Gaussian and kind of like squishing it like, Play-Doh into the right shape in a continuous way. And at the time, this was like a huge freedom because we could just use any old neural network to specify these dynamics. The density models people were using back then had to somehow like partition the dimensions of your neural network and had to have all these restrictions. And this even scales to images, or at least this is like again like 2019 or 2018, showing how we take initial Gaussian noise and then gradually convert it into images. And then of course we can also interpolate in the latent space to interpolate between images. Okay. And other people besides me found like nice applications of this setup. For instance, this point flow algorithm said in 3D modeling we often want to specify a non-intersecting shape. So we could, and that's actually kind of hard to do, or it was hard to do at the time. But one nice way to do that is to start with a sphere or something that's non-intersecting and then locally deform it according to an ODE. And you'll never be able to actually make that shape intersect itself as long as you're following that ODE. And of course, now we have implicit surfaces, which are maybe a really even nicer way to do this that has been developed in the short time since then. Okay. And again, for like perspective, there was some follow-up work done by me and others that said, oh, inspired by these continuous time flows, we can actually find discrete layers that are invertible, which is kind of what we wanted, and allow us to have this like free form Jacobians that don't require any sort of special structure. So we were able to take inspired by the continuous math, go back to discrete time, which is a lot easier to handle because you don't actually have to have a fiddly ODE solver in the middle. Okay. And as we all know, denoising diffusion models, partly developed here at Berkeley, are now like the state of the art in large image models. And actually, I wish I had included some of the 1,000 by 1,000 pixel amazing high quality images, but I'm sure you guys have all seen stable diffusion. Yeah, this family of models is actually a continuous time generative model. And you can decode from them actually by following one of these continuous normalizing flows. Although sometimes people just treat it as an SDE too. So that's kind of cool. I feel actually really dumb because I worked on all these different applications of continuous time models, and I did not see diffusion models coming. I thought that they were silly because their posterior is so simple. But I actually had already written a paper about how you can make up for simple posteriors with really expressive decoders. So I should have known better. But anyway, it's still gratifying that people built on this stuff a little bit. Cool. So now I'm going to get to the sort of, I don't know, the good part of the talk, where I'm going to show you an application where I really think that these continuous time models are going to be the undisputed king in some senses for the foreseeable future. Obviously, that's a very strong statement to make. I'm being hubristic by saying it, but I think it's true. And please tell me reasons why it's not, right? So one of the motivations for why we need natively continuous time models is that real data often comes irregularly sampled through time. So at the top here is data from a patient's stay in an intensive care unit over 48 hours. And the black marks represent when somebody took a measurement of this patient. And there's different types of measurements they took at different times. But the point is there's no camera feed with regular 60 hertz updates. There's just doctors and nurses coming and going and taking different measurements. At the bottom is data from brightness or spectra of quasars taken by telescopes. And there's seasonal gaps and all sorts of reasons why the telescopes can't just point at this one quasar all the time. And most of the large parametric models we have, like RNNs or transformers, really want you to somehow bin your data into discrete time. And you can kind of shoehorn continuous time in as an afterthought, but it doesn't usually form a coherent joint distribution over your data. So how can we handle this data without ever having to bin or do imputation or averaging? Okay. The other ingredient that we're going to need here is latent variable models. And for some of the people in this audience, this is their bread and butter. And it's insulting to introduce them. But I feel like for anyone who hasn't learned the gospel of latent variable models, it's worth spending just a minute saying that this is kind of one of the most natural models we can ever imagine because it matches the structure of life. What these models say is that there's some hidden state of the world, which we can't directly observe. There's some transition dynamics that tell us, or that say how the state updates at every time step. And then sometimes we see some data that depends on that hidden state. And often we say, oh, this is a noisy version of this hidden state, but it really could be anything. So as a concrete example, we can imagine that Z here represents the state, the physiological state of a patient in a hospital. And it's updating according to whatever disease they have, and maybe also we could add some nodes for we give them a drug or some surgery or something. And then maybe these X's are doctor's notes or X-rays or some heterogeneous mix of all the sorts of partial observations of the patient's state that we get at different times. Classically, the model that people mostly used was Kalman filters, where everything here was linear and Gaussian. And now, just in the last few years, we can say nothing has to be linear, nothing has to be Gaussian. We can make all of our transition dynamics learned in some free-form way, or structured if we know what the structure is, and our likelihoods, again, also learned in some free-form way. Maybe they're a language model for the doctor's notes. Who knows? The point is, this is a very modular architecture, and you can kind of stick almost anything in here. And it's a good match for reality. The only problem here is that we don't directly observe the latent trajectories, and we usually can't even estimate it very well. There's usually at least a few details that we won't be able to keep track of with any fidelity. And so if we want to compute the likelihood of our data, do maximum likelihood training, we have to somehow integrate over all possible trajectories that this system could have taken. So I won't have time to get into approximate inference for this audience. We're going to use variational inference, and I'll show you some examples of that in a minute. anyway, this is the way, the truth, and the light. Let me just leave it at that. Okay, so if we want to make these models continuous time for real, we just need to have some latent variable that changes according to some differential equation or some instantaneous update. So the first model we tried was this ODE latent variable models that says on your first day in the hospital or whatever, you have some latent state, and then there's some function f that will learn, that will tell us how that state changes deterministically through time, and we will be able to condition on some observations at different times. And these can come at any time, and there's no problem with missing data in latent variable models. If there's data that you could have seen but didn't, its likelihood integrates to 1. It's the exact mathematically correct thing to do, to just leave it out of your model. You never have to do any imputation. It's beautiful. It's one of the main reasons why we should use this framework. Okay, and this model has this like well-defined state at all times. We might not be certain about it at all times, but it's like at least meaningful. Okay, so that's all very abstract. Here's just a toy example of us jointly fitting the dynamics of one of these models and the likelihood and integrating over the latent states. So what I have here, these little green dots are data, like noisy data. These are sort of trajectories, which we don't see sometimes, maybe because our telescope was off or something. And then there's like 3 different trajectories. So these all share the same dynamics, but they don't have the same initial latent state. Here we're showing the trajectories of the latent states, which are just garbage for now. This is all at initialization. We haven't learned anything yet. And this is the dynamics function, that f. Here the observed state is 1-dimensional, and we've made the latent state 3-dimensional. But there doesn't have to be any matching between these 2 things. They don't even have to have well-defined dimensions, just well-defined dynamics and densities. Okay, and so this is just a 2-dimensional slice of this dynamics function that is from 3 dimensions to 3 dimensions. And we're going to throw this all into a giant soup of gradient-based optimization with variational inference to handle the fact that we're uncertain about stuff. And it all magically works thanks to the power of gradient descent, which works better than anyone had any right to expect, as Jeff Hinton says. Right, and so here it's doing the nice thing. It's learning some sort of periodic dynamics that kind of look like a spiral or something. You can see the latent states going up, going in circles, and then this matches the data. Right? Yeah.
So the loss function here is squared loss.
So the loss function here is we're maximizing the marginal likelihood.
Oh, so you have an observation.
Yes, exactly. Which happens to be Gaussian for this example. So it actually is a squared loss in that sense.
But in general, would it be a neural net in general, or?
It can be any likelihood that has parameters that are differentiable with respect to the latent state. Yeah. Oh. Yeah.
For a physical system, like the dimensionality of z would be very, very large, and oftentimes observation, the dimensionality of x would be much, much smaller. Thinking about like, in that case, wouldn't it be horrendously complicated to do neural ODE on Earth state z, and instead like maybe do some, I don't know if you're familiar with statistics, like some Mori-Zwanzig operator things to get the cap differential equation for you.
Yeah, thank you so much. So the question is, yeah, what if the latent state is really high? And also, shouldn't we be using SDEs? So I totally agree. And so the 2 slides from now is we're going to use SDEs. So anyway, so I want to say, so we tried this latent ODE model on some real medical data, and of course, it sort of won because it was sort of like type correct, right? We could do whatever everyone else was doing already before with RNNs or VAEs or whatever, and just make it actually match the type of the data. So we couldn't not win. One thing I want to mention for those is we can also condition on the fact that an observation was made using a Poisson process likelihood very easily with this framework. So the fact that somebody even took a test often tells us a lot about their health, right? Like healthy people don't get a lot of tests. And that's just something that didn't help much in this instance, but is a really nice thing that you can do with this framework. Okay, so one point I want to make, for those people who are really big on deep learning and not on probabilistic modeling, one other alternative, in fact, we tried a lot of RNNs as baselines, and they worked moderately well. They're very simple. They're probably the first thing you should try because they're so simple and easy to use, and they can be adapted to continuous time as well. And they have this hidden, RNNs, taking the data and have this hidden state. But this hidden state is not directly a representation of the system that the RNN is sort of observing. It's a belief state. It's more like if I was watching a baseball game and then you came and like scanned my brain, I would have some knowledge of the game, but I would also have like my own uncertainty about what's going on would be part of that state, and it all mixed up in a big jumble. So these states are sort of like less interpretable just by construction than those of a latent variable model. The other problem with RNNs is that they don't actually take advantage of Bayes' rule. So they have to learn to do inference from scratch, whereas if I have a Bayesian model, if there's a situation I haven't seen before, but I do know the prior and the likelihood pretty well for that situation, I have all the tools I need to get a good, well-calibrated prediction, even if I haven't seen that at training time before. However, so that makes RNNs more prone to overfit, but they're also more robust to model misspecification. There's not really, you don't have to worry about getting the prior right or your approximate inference right, which is a huge, huge benefit in practice. Cool. So obviously, latent ODEs are kind of limited because everything proceeds deterministically from some initial state. And if in this model, if you get hit by a car when you're 20, it has to be somehow like foretold by your initial state that that's going to happen, which means that the initial state gets huge and gets slow, as the audience member suggested. So we would obviously like to have some sort of stochastic transition dynamics that represent all the slings and arrows and minor perturbations of our state that we weren't able to directly observe, just like the discrete time ones do. So if we took this discrete time latent variable model and took the infinitesimal limit of the step size, we actually recover exactly stochastic differential equations, like the exact same ones that numerical people have been using for physics for hundreds of years. There's a few papers that, like, in deep learning that kind of claim that things were SDEs when they were just actually inventing a different model class. These are like the standard old school kinds, and they, just like ODEs, they have a deterministic part, and then they also have this diffusion part that adds some infinitesimal noise at each step. And so we can also parameterize the scale of that noise at every step with the neural network, and then this is like a neural SDE. And this defines an implicit distribution over functions where I could start at some initial state, sample my entire noise, follow these dynamics by some solver, and this is kind of like Gaussian processes or something like that, but much more flexible. So one thing people say when they see SDEs is they say, oh, you have this noise is Gaussian instantaneously. That's kind of limiting. It turns out that's not actually the case. These are sort of, having Gaussian noise here is still universal in a technical sense. And we can express all sorts of non-Gaussian distributions over functions with just instantaneous Gaussian noise, as long as these functions are nonlinear in the state. Yes? Well, yeah, so there's a stronger sense in which also adding Poisson jumps makes this even more universal. I just mean, actually, I don't think I could concisely say in which sense we're universal when we just have Gaussian noise. But the point is, if I made this instantaneous, like Bernoulli noise or something, that would be equally powerful. Or like, it would also, it would be equally powerful. Okay. And it's good for any time there's like many small unobserved interactions. And we can even shoehorn like large interactions into these models, although obviously for full generality, we'd like to have like some sort of instantaneous jumps as well, which we totally can. And that's like a good extension of this approach. All right. So the model that I think people should be using, and that they're just starting to because it's just become practical, is latent SDE models, which, as I said, have are just like the latent ODE models, except with instantaneous noise at each time. So here's a simple graphical model where we have our initial state, and then we have our updates, which depend on an entire Brownian motion draw, like an entire function of noise that's sort of like infinitely detailed. And again, a likelihood, and again, this could be a language model for doctor's notes, whatever you want. And the cool thing about this is that we can integrate over all the latent trajectories conditioned on the data in a very natural way that is like sort of simple and universal. So normally when we write down a probabilistic model, we also have to choose some sort of sampling procedure or a family of approximate posteriors that are going to approximate the probability of z's given the data. And this is like this whole game of the more expressive you make it, the more expensive it is. Often people end up just using Gaussians because it's simple and fast. It turns out that there's sort of this one natural choice to use for SDE posteriors, which is another SDE that shares the same drift function. It has to, or else the sort of divergence between the prior and posterior is infinite, but has some parameters that we can learn. So the general recipe here is that this prior is going to be given to us. Maybe we can learn it from data, or it'll come from nature, like it's some like stochastic Navier-Stokes or who knows what. And then when we want to condition on data, we're going to optimize the parameters of some neural network that's like very free form, that's going to specify all the details of our posterior. That's very abstract, so here's a concrete example. So here's some data in one dimension. We haven't conditioned on it yet, but this is, I'm showing you the prior SDE. So these little arrows are showing you the drift term, and then at every point we have sort of noise. So this drift term is kind of making all the trajectories want to head towards the mean here. This is actually an OU prior. And then the diffusion is kind of making it spread out. So it spreads out until it hits the diffusion or the drift term, and then it kind of goes back in. And now I'm going to show you optimizing a neural network to specify the posterior over trajectories to maximize the marginal, or the elbow, a lower bound on the marginal likelihood. So I'll just run that one more time. Right, so again, we're using stochastic gradient descent. And we are, and I'll show you exactly what we're optimizing in a second. But the point is that after we've run our optimization, we have the parameters of this SDE, which change according to time. They're like pretty detailed. And they give us the posterior, which does the sensible thing. It's uncertain where the data, where there's no data. It's certain where the data is, right? It's exactly what you want from a posterior. The term that we're optimizing is the likelihood plus this sort of instantaneous KL divergence that says how much does the posterior dynamic drift differ from the prior drift. So this is basically a regularization term, you can think of it, that wants the posterior to look like the prior, but also to match the data. And so just to see what this looks like, this U term is sort of like high around the data because the posterior has to steer the trajectories to match the data or give high likelihood, and then it can kind of relax after it's seen the data and go back to the prior drift. Cool. And yeah, here's like a toy application to mocap, just to emphasize this is not for one-dimensional data. It's for, it can be high-dimensional data, high-dimensional latent space. There's no problem with that. OK, so I gave a talk about this stuff a year ago at the Flatiron Institute, and some people at Stanford and Columbia said, oh, this is a perfect tool for our application to quasar data. And again, they have this real quasar data. They know that there's some relationship between how the brightness varies and like the mass of these black holes or whatever, but they actually don't know what it is. And so they can't just like write down their SDE in closed form. And again, like we have irregularly sampled data. So they thought this was going to be a perfect fit for their approach. And so far they've used it on actual, well, they've made synthetic data and shown that they were able to recover with appropriate uncertainty the true mass and other properties of their simulated black holes from their simulated data. So I was not actually involved in this work. They just were nice enough to send me these slides like yesterday because they finally got it working. But the point is like this, I think, is a great match for like a lot of real scientific problems. OK, now I'm just going to, for those of you who know about approximate inference, I'm going to give you a couple of reasons that surprised me why this is an even nicer model class than just for the reasons that it like fits the type of the data. So number one is the main problem with all of this is that it's slow compared to just choosing a fixed discretization. However, we can add a little regularization term that's not very impactful that makes the dynamics easier to solve by whatever solver you happen to be using. And the form of the regularization that helps the most depends on the strategy of your solver. But on the left here, we have an example of we're learning a function from z at the bottom, t0 to t1. And we just minimize the squared loss between these input points and these output points. The dynamics that we use to get there happen to have all these crazy curves and bends because they're not hurting anything in terms of accuracy, but they are hurting us in terms of the number of function evaluations that the solver needs to make. So we just said, OK, let's regularize. This is the we regularized, I think, the fourth derivative of the these, like the curvature basically of these trajectories, which we highlighted in red where that's high. And now if we take the same loss and add just like a tiny bit of regularization and we train it some more, all the lines sort of straighten out and the number of function evaluations also decreases. And again, we have this like Pareto front of we can turn up this regularization, and initially it just makes the dynamics easier to solve without hurting our accuracy at all. And then at some point it does make the accuracy worse, which makes sense. Okay, so that's like one answer to if we think things are being too slow. But it's not a good answer if we really think we have like physics or some like true dynamics that we really believe in and we don't want to like fiddle with them. Oh yeah, and but I will say if we have a latent dynamics that we're learning from scratch, usually there is like a slight variation on the unregularized dynamics that gives you like much faster solvers with like only like a small payoff in loss. Like again, it's like a Pareto front. Okay. So the other cool thing that we get when we move to this like continuous time land is zero variance gradients, at least asymptotically. And like, that might sound too good to be true. We won't get there exactly. But it's building off of a trick actually from a paper I did in 2017 where we changed the gradient estimator for variational inference to be asymptotically zero variance as you approach the true posterior. So what does that look like? So here on the left, the variational inference tries to optimize one distribution to look like another one by randomly sampling from it and sort of checking locally if the distributions match. But because you have to randomly sample, the naive way of computing gradients actually gives you variance in your gradients all the way, even when you're really close to the true solution. So your optimizer bounces around forever unless you decay your step size, which is annoying. But if you use just a slightly different gradient estimator, just removing one term, then the closer you get to the true posterior, the closer your gradients get to zero, and you stick the landing and stay perfectly on the true posterior. So that might sound too good to be true. I think it's not, because it does require us to find the exact true posterior, which we know is hard in general. But it's kind of nice because as you get, you don't have to get all the way there. As you get closer, your variance is going to go down. So we worked out an extension to this for stochastic differential equations. So if we make our approximate posterior expressive enough, we can get arbitrarily low training gradients. Yes, question?
What was the one that
it was, there's two ways in which, actually, I'm going to explain that after because we're almost out of time. Yeah. Anyway, and so again, here I just want to show you, here's us training in approximate posterior. And one thing I want to emphasize is that these posteriors are non-Gaussian. They can be multimodal. There's basically, again, I'm not sure I can articulate here with the sense in which they're universal, but we can certainly make them like really look like any true posterior if we give the posterior dynamics enough parameters. Cool. And then this is the thing that I'm most excited about, which is that I think this framework gives us a principled way to avoid simulating the low-level irrelevant details in any simulation where there is some like high-level state that can summarize the important parts. So here's this slide I showed you before about the posterior dynamics and this sort of instantaneous KL that we're paying between the prior and the posterior. And it goes to zero when we're sort of between data points. Right? And this makes sense. Like if you can imagine if we're like running a numerical weather simulation and we have lots of weather data at one time and lots later, we might want to somehow skip over all the details, especially if we think that they're going to somehow like mix out. So it turns out that you can exactly do this in any SDE that has a stationary distribution. Is you can just stop simulating as soon as you've like hit the last data point for a while. And then the only trick is you have to somehow, and you know that the KL divergence is going to be exactly zero in between, and that you've mixed, so you don't have to store anything. And the only trick is you have to somehow fade in right before the data with enough time to like steer your trajectories to match the data. So you can kind of think about like dreaming. Like sometimes in your dream, like something is set up and then you skip way ahead, and then you somehow are able to like envision this coherent like details that mesh with the overall narrative of the dream. I think this is a way we can do this automatically in variational inference. And one of the nice things is that a few years ago, Emily Fox actually worked out a complete recipe for all the dynamics of SDEs that have a stationary distribution. And so the details of this don't really matter. Some of these are skew symmetric. But the point is, if we parameterize our approximate posterior this way with like neural networks to give us all these matrices, we will have sort of the full class of distributions that have a stationary distribution, and we know what that distribution is. So at this point, you should be saying, well, but what if there's some sort of long-term memory in my system, right? Like, if I just forget the details, it can't be that interesting of a system if it's like somehow memoryless. And the answer is, that's fine. We can just introduce auxiliary variables into our approximate posterior that weren't there in the prior. Like, we can imagine adding like temperature and pressure to our simulation of a gas. These are like imaginary quantities. They're not in the original prior, but it's totally fine to add them to the model. And then let them keep track of all the sort of slowly changing important details, conditioned upon which all the low-level details will quickly mix away. And it's kind of nice that if you have this graphical model for, here's the slow variables and then the fast variables that depend on them, the sort of instantaneous analog of that is this pair of stochastic differential equations. There's a whole language of whatever structure you think you want to add to your posterior compiles down automatically to some equivalent structure in the stochastic differential equation. So what we should be able to do with this is imagine we're like, measure an infant's heartbeat. We can condition on that data, add some sort of like slowly changing auxiliary variable about like the overall size of the infant or whatever. That's going to be very easy to simulate for like months or years ahead, super slowly changing. And then condition on that, find the stationary distribution at the next time we want to analyze some data, sample from that distribution, and just pick up where we left off, having skipped over simulating like years of individual heartbeats. Yeah, so we just started coding this up. I just finally found a student who like has all the expertise in SDEs and variational inference and neural networks to actually get this working. So we're at the stage of doing this without the high-level variables. We're just about to start doing sort of toy experiments in this setting. Okay, so that's the takeaway is there's this newly practical class of latent variable models that are natively continuous time. They can handle any sort of realistic data that you might have in principle. And I think people haven't quite taken advantage of these yet. And there's code both in Torch and in JAX for doing approximate inference in SDEs. This is like pretty new. Again, in practice, you should start with a recurrent neural network. So I'm just going to go like 3 minutes over time to tell you like what I'm excited about. So one is, where I want to take this next is to also have things factorized spatially so that we can do the kinds of multi-resolution approximate simulations that numerical weather people do or molecular dynamics people do. Of course, I'm not really an expert in stochastic PDE solvers, and I would love to chat more with people here who know about that. But I think that a lot of the sort of hand-tuned heuristics could be put into one of these frameworks where everything is sort of jointly tuned, is much more fine-grained and adaptive. So deep learning people are already on the case here. This is a figure from a paper about like how can we bring probabilistic methods and deep learning to numerical weather prediction. I'm not the only one talking about this, but most of the work so far has said, okay, let's just replace a huge chunk of this with a neural network that takes in like observations and outputs predictions, which is fine if you have like really regularly sampled data and you're not really, well, I claim it's not going to generalize as well as if you use a latent variable model instead. And then the other thing, one of the enabling pieces of technology to get all this stochastic gradient stuff to train was a way to sample an entire set of Brownian motion noise in a fixed way that you could query at any point at arbitrary resolution. Normally people will just like start at the left and sort of condition on what they've seen before. But if you have to do gradients and go backwards and reuse the noise, or you have adaptive solvers that have to query in all sorts of different places, then you either have to store everything and, well, it gets hairy. It makes your solver much more complicated to implement. And it's actually much worse in like multiple dimensions. So we worked out this algorithm called the virtual Brownian tree, where if we want to sample Brownian motion, we first just sample the endpoints. And then given a query time, we iteratively bisect the interval keeping track of making our random seed depend on which branch in this tree we're in, so that everything is reproducible, and we can sort of zoom in exponentially fast on any particular time. So this is like a fun sort of like lazy data structure, but it's like a lazy stochastic data structure that lets us sample an entire function sort of exactly without having to evaluate it anywhere. And then just like a month ago, I worked out how to do this recursively so that this applies to Brownian sheets in any dimension. And now I think that this will let us sample infinitely detailed noise that we can zoom in on any point we want, zoom out, never have to store anything. So here is one such zoom into one particular infinitely detailed function that we can just keep zooming in to forever. And then, oh, I hit the Planck length there. It's like numerical floating point underflow. Anyway, so I think this should allow simpler adaptive stochastic PDE solvers. And I also am working on taking diffusion models like stable diffusion and saying, let's actually train this on data at multiple scales, including like microscopic images of skin or whatever, all in one giant model that's like infinitely detailed, but that we only query at a particular resolution and let some adaptive SPDE solver sort of fill in the details. And if we want to keep zooming in and find out like what the little blemishes on someone's skin look like for a particular example, we can just tell the solver to refine those areas. That's the vision. A long way to get there from now. Okay, and then the very last thing I want to say is, from my discussions with people today, we're in a funny moment in history, right? Where I'm saying, let's use these compact latent variable models that are kind of like the old like Chomskyan, things that humans could understand and are sort of legible and make sense. But I'm kind of on the wrong side of history, right? Right now, what everyone is excited about is that, no, let's just have one giant autoregressive model that slurps in all the data, and if it doesn't work well enough, find some related data to give it. It's going to be fine. And this is really nice for some reasons, like it's robust to model misspecification, and it wants to learn, as Ilya would say. But like getting uncertainty from the model is like very like indirect and hacky. So I realize that, again, I'm like on the wrong side of history, but I kind of think it's at least worth it for scientific application. All right, thank you very much. Yes.
Can we use the box here?
Just be loud.
So, so one of the key areas where I see this difference between discrete and continuous as being very annoying is reinforcement learning versus control. So classical control always has differential equations for the dynamics, and RL people do everything with discrete states. Even when it's large and they're using neural networks, the point is the states are discrete. So have you sort of adapted your work to, or encouraged anybody to work on using your models for capturing dynamics in that setting?
Oh, great question. So I totally think this could all be adapted to control. And in fact, one of the first things, like actually 2 years ago, I saw Sergey Levin, and I pitched this idea to him of the multi-scale thing. And he said, oh yeah, like, your robot wants to plan and it has to open a doorknob in some like really detailed simulation. Then it wants to like walk across a room in like a very coarse simulation and then zoom in again and like imagine opening the other doorknob. So that's ultimately where I want to take this. I will also say that Sergey made a really good point, which is that you could also do the multi-scale stuff in discrete time. And he's right. And in fact, there's been some related work like clockwork VAEs. And I would say the only problem there is that you have to choose a discrete downsampling level. Like they choose like 8 times downsampling at every layer. And it's not adaptive. So if there are some times when the high-level variables change quickly, that's not going to play well with one of these pre-chosen discretizations. I hope that answers your question. Yes. Oh, yes.
The term that you described. The question I asked before about the term you described. I was wondering about the term you discarded that made it work better.
So basically, when you change the parameters of the approximate posterior, one of them moves the sample like left and right, like where the sample is, and then the other one changes the height of the density at that point. And I'm actually having trouble remembering which one we removed. I think we removed the one that adjusts the height of the density, but to be honest, I hadn't actually thought about it in a long time.
Is it significant? I mean, which it is?
Yeah, yes, only one of them, only removing one of them gives us a 0 variance
Is
estimated.
it about the algebraic variance of it?
It's just that one of those terms actually has expectation 0, so you can safely remove it, and then it happens to have this nice property. Stuart?
Thanks. So I'm wondering, I mean, it has some family resemblance to the neural operator ideas that Andrew Stewart and Anima Anand Kumar and others are doing. So they're sort of doing something with PDEs and continuous time, continuous space, no discretization. So is it just a family resemblance, or there is something deeper here?
I would say that there's a divide, which is one is I'm using black box adaptive solvers for everything. So I'm writing down these models in continuous time and always delegating across this iron curtain to this model or this solver whose details I don't need to know or care about. And then I'd say Anima, for the most part, is on the other side of this curtain, saying I'm going to use neural networks to speed up these solvers. And so if I've seen many similar PDEs, I can somehow leverage that or amortize my solutions. And so that's like, again, really useful and complements this work. But I think you can do these two things totally orthogonally. Yep.
So towards the end, you were talking about also having what sounded like adaptive resolution in the spatial dimension.
Yeah.
Is that sort of an analog to the adaptive resolution in the time dimension, where you're also plugging this into a PDE solver? And
yeah, so I'm hoping that'll be the analog. But to be honest, I'm a beginner at PDE and especially stochastic PDE solving. So it's one thing. It's actually a lot harder to define like densities on functions. So there's been a few papers recently talking about viewing stable diffusion and stuff like that as some sort of PDE or SPDE, and they always take some sort of shortcut. I don't think anyone has the measure theory chops and the deep learning chops to really like make some coherent model out of this thing yet.
Yeah, I was kind of just wondering if there was a established framework for that.
No, I mean, surprisingly to me, no. Like I keep expecting somebody to come along and say like, oh, this is just, from control or whatever. And I hope that they do.
Right, thanks.
Okay, great. So let's empty.
Yep. Cool.
If you could know your way back to either my building or your host. So
yep.
basically the reservations